work. But what I'm going to do is try, if this works here, try to take you through exactly what we're doing, why we're doing it. So normally, in most circuits, you have a digital clock. Matter of fact, in almost all circuits, your computer has it, your phone, it's a digital clock. That's the thing that causes the problems. So if we talk about the voltage, it's actually the current too, but we're going to look at just the voltage waveform. Typically, you're going to have something that has a certain rise time, and it's going to have a certain level of on time, and I'll get to that. I mean, we've gone through this one time, and this signal repeats itself as such every tau. So this amplitude here would be A, and I call this X of t. It can be a voltage or a current. Typically, though, it's a voltage. And from the 50% point of the on point to 50% down, that's labeled as tau. The actual period from here to here is labeled as t. Sometimes it's called a pulse repetition interval. All right. T is actually equal to 1. Really, let me do it this way. F naught is the fundamental frequency, and it's 1 over t. And omega naught is simply 2 pi F naught, and that's 2 pi over t. This is the fundamental frequency in radians per second. This is in hertz. But F0 means fundamental frequency. Now, you've seen this before. When you had digital, did he go through a waveform analysis like this or not? Did you have Dr. New for digital electronics? Didn't he go through this with you at some point, or something similar? Did he talk about duty cycle or duty time being equal to, called duty cycle, as tau over t? It's really the time on versus the total time of the pulse. Do you remember this duty cycle? Did you get this in in digital electronics or in digital, in that, what do we call the thing where the JK flip-flop things and stuff like this? Did you have, you had this, what course did you get that in? Just tell me.
Probably digital electronics.
With Dr. New, right? But he must have gone through something like this. All right, because these are actually exponentials, but this is the very early part of the exponential, and this is the very early part. They're not exaggerated like that. This is just basically an exponential decay, but it's just the first part of it, so it's much less than several time constants. So if we have that waveform, we know we can express it as a Fourier series, right, and a Fourier cosine series. But the real thing we want to do is take a look in the frequency domain at what the signal spectrum looks like. So if we take a look at this in the frequency domain, and on this axis we're going to plot 20 times the log right here, and this is going to be the magnitude of 2 C of n. Now remember that C of n here represented the coefficients of each one of the cosine series. Do y'all remember this class? I took you through it last time. I'm just trying to bring you up today. Now here's what it looks like, and this is important. This is where you start paying attention. And the one other thing too. I'm going to do this. I was going to do this in a different way, but let me just say one thing about this. Normally, on that axis, it's dB microvolts or dB microamps, usually. So on this axis, they usually plot 20 times the log of the magnitude here of the coefficient C of n, really here, times 2, but it's over 10 to the minus 6. And that means this is going to be in dB microvolts. All right? If you have something that's a regular voltage, you divide it by 10 to the minus 6. That's microvolts, all right? That's the level of microvolts. And then you take 2 times the magnitude of this. So what does this look like? It'll look like this. It'll keep flat here. This level will be equal to 20 times the log of the magnitude. And here, it will be the magnitude of A times tau over t times 2. Now, typically, tau over t is 50% or 1/2, so the halves and the 2 cancel. So it's just 20 times the log of A, but then it's divided by 10 to the minus 6. So that's what this represents, this part of the curve. I did this last time. Do y'all remember when I was doing this? I showed you this. Now, the first frequency you worry about is, I call it the first break frequency. It's really due to the length of on time, tau. And that occurs right here. And that will be equal to when f, and I'm plotting versus f for a reason, is equal to 1 over pi tau. That's the first break frequency here. And I'm using terms that I feel comfortable with. They may call it something else. It's a frequency where all of a sudden things break off and start going down. Now, this will start having a slope here of minus 20 dB per decade. Remember, this corresponds to that waveform, and that's the key part of it. This is in the frequency domain. We're looking at the voltage spectrum versus frequency, right? Not power. Can you all understand this, class? Are you with me with this in the back? Follow me? All right, now it's going to keep going down until you hit the second break frequency. And this break frequency will be 1 over pi tau rise, right there. Now, if we were plotting versus omega, there would be a 2 pi down here. Or I mean, a 2, pardon me. There would be a 2 down there. But actually, it would be those multiplied by, or let's see, yeah, multiplied by 2 pi. So don't worry about this. Normally, they're put in frequency, and that's hertz. It's just the normal way. How many have seen a spectrum analyzer or a network analyzer being used? Do any of your laboratories use this or not? Radio lab, perfect. So you at least know what I'm talking about when I'm talking about sweeping the frequency and looking at that curve. This is the typical way you do EMC analysis. This is actually the signature of, if you took the frequency spectrum of that signal generator, this would be the envelope. Actually, I'll mention something in a second. Then after this frequency, it starts going down at minus 40 dB per decade. All right? So there's the first and the second. Last time I actually did the proof on this one. And really what's happening here, to be frank about it, is this is an envelope. There's a whole lot of oscillations, but when we do EMC analysis, we look at the possible worst case effects always. This will be the yeah.
So that's why you don't have the cosine of...
You don't, no. We absolutely know they'll be at distinct frequencies. But the thing is, this is the envelope that you worry about when you do EMC analysis. You're always looking for worst case effects. This is the worst possible signal, or spectrum of the signal that comes off of that. And that's the way you do it. Now, when you have that thing, all right, and you're doing an EMC analysis, now everything is done normally with in the domain, not the linear domain, but with everything's going to be 20 log of something. So we're going to be in the logarithmic domain. So now I gave you several problems. I don't know if you looked at them. The first problem, I'm just saying, I gave you, I asked you to calculate the Fourier. Didn't I ask you for a few of those Fourier coefficients too, just to start class? I asked you to do, I'll go to those in a second. Move it down a little. Keep going, keep going. Keep going, stop. Now, see problem, that's 22, right? Or 2.2? This one.
3.22.
All right, 3.22. I want to do this one. He says that, right here, just leave it there, that you've got a signal, and what he's done is, for the signal, it's that exact signature, and I'm going to put the values in here. Oh, he leaves it in terms of omega, that guy, doggone it. All right. I'll put it in terms of omega instead of f, but it doesn't matter in this case. So first, this has a magnitude of what? What was it, 110 dB or 120?
120.
So it's 120 dB microvolts right here. That's the base level here it's coming out at. Then this frequency is an omega, unfortunately. And I don't know why I did that this way. But the first frequency, the first break is at what?
First break's at 10 to the 6.
At 10 to the 6, so omega equals 10 to the 6 radians per second. If you wanted f, you'd have to divide that by 2 pi. The second break is at where?
20 times 10 to the 6.
And that's radians per second.
Yes.
Now, important, you notice the only thing I did here was I adjusted for the amplitude given in the problem. All these problems will have that same signature for the input, the clocking pulse, all right? That's always the way it is. I'm just adjusting the thing. And unfortunately, almost everything I've ever seen is done with f. In this particular problem, he chooses to put omega, it doesn't matter. Now he says this is the input. So this is our, you could think of it as our x of omega. I'm in class. And this is my fault for not turning that darn phone on. When I was getting here today, I didn't realize that they were doing all that tailgate stuff and putting things up, and I got jammed up behind people and sort of locked out of the library. All right, so with this one, this is the input, and here's what it looks like. I have my input spectrum x of omega. Think of it this way. I know it's in dB. Now I have a system, h of omega. That's a standard transfer function. Got me? And we have my output right here, y of omega. Now, normally, y of omega is just x of omega times h of omega, right? Just follow me here. Oh, gosh. So this is equal to x of omega times h of omega. Now, if this is linear, right, the input here would be 20 times the log of magnitude of x of omega over 10 to the minus 6. That's what we have there, right? Right? The output itself, if I do logarithmic scale, it's 20 times the log of magnitude of x of omega times h of omega. I'm doing this for a reason this way, so you see it, divided by 10 to the minus 6, right? I want everything in dB microvolts. Do you follow me? So now I'm taking the log of that divided by 10 to the minus 6. If you watch this stuff falls apart. Now, if I have log A, log B, it's log A plus log B, right? So now I have 20 times the log of really the magnitude of x of omega divided by 10 to the minus 6 plus 20 times the log of magnitude of h of omega. The 10 to the minus 6 is over only one of these. Now, isn't this the exact signal as this right here, right? It is the input signal. It is, in fact, what this represents, this curve here. Do you all see this, class? Make me see your hands. Do you understand this? I want to make absolutely certain there's nobody that doesn't understand this, because it is not in the book. So this is important that you watch this. Yeah?
So what does that mean? That's the output.
This, yeah, and this is, see, this is just the input, all right? The only thing we're doing is now not multiplying, but we're adding 20 times the log of that, right? Now, in his book, how he shows h of omega for this problem, and I'm going to have to do it here, he goes ahead and he takes the log and he puts it where omega here is logarithmic scale, just like that is logarithmic scale. You know how the paper takes the log on this one, right? And this, we take the log on and plot it. Follow me, class? Now, if you look at that, it starts at what frequency? Give me the lower frequency right here.
The lower frequency of that's 10 to the 5th.
So it's 10 to the 5th radians per second. Then there's 10 to the 6th, 10 to the 7th. But the thing that's consistent is the rate of increase. Is it?
It's plus 20.
So he's saying it's going to increase. This is h of, it's really 20 times the log of the magnitude of h of omega. And it's going to, where does it start in at? You got minus 30 dB, and it keeps going up at a rate at plus 20 dB per decade. And that you'll see all the time. You'll see 20 dB per decade, 40 dB, either plus or minus. When you get higher order filters, you'll see 60 dB, 80 dB rate of change. So just get, it's usually 20s, 20, 40, 60, 80, stuff like that. That's what you see, either plus or minus. So now when we want the output, the input, and I'm going to make this a little cleaner here for you to see. I'm just going to redraw this so I can show you how easy this is in these problems. And we'll do several of them. That's where you'll actually learn this. What he's actually got, if you look, he has something that looks like this. This was omega 10 to the 6th. This is omega equals 50 times 10 to the 6th. Is that right? Right? Oh, it's 20?
That's 20 times 10 to the 6th.
This is 20 times 10 to the 6th there? Okay, sorry. And here was 120? 120 dB microvolts. Make sure you put dB microvolts. And this is x of omega. Now, if I take a look at that filter business right below it, right here, it starts in at omega is 10 to the 5th, and the level here is minus 30. And it just straight up at plus 20 dB per decade. All right, and that's just versus omega. Do y'all follow me? I've stacked them like this just so you can see it. Now, how do we get the output? We start right here, right? And our output, I can't work it in here for you to see it, so I'm going to have to put it over here. And I'll put it right here. So here, this is omega, and this is going to be a 10 to the 5th here. I come up, and I take a look at this. I've got minus 30 that I'm going to add to 120. Does everybody see that? Just atoms. So that's going to be 90 dB microvolt. Correct, class? So it comes in at 90 dB microvolt. Now notice this is flat here, and this is increasing at 20 dB per decade. You all see this? So it's going to keep going up at a rate 20 dB per decade, right? Until I go exactly 1 decade down at 10 to the 6th. Correct, class? Please watch this. You all agree with that? Now, at 10 to the 6th, it's gone up a decade. We've gone a decade in frequency. We've gone up 20 dB, right? So here, at 10 to the 6th, now my level is going to be 110 dB microvolts. Do you all see that, class? Just make sure you see this. It's not in the book, and I'm trying my best to make sure. I know there's distractions, probably gambling sites, all the other things. And there's a football game, and I don't know if sports betting's popular with you guys, but I know with some groups I've had, what is it called? Fantasy football with the NFL too? And that's the other one. They got some college football version in it too, whatever it's called. Anyway, it goes up to that, right? Now, you'll notice now this one starts going down at minus 20 dB per decade, right? The rate of increase is canceled by this, so it's flat here, just flat. It's flat until it hits this point. Now, this is important what I'm going to tell you. So at that point, comes up, it's flat until it hits wherever this is, 20 times 10 to the 6th. Remember, that's logarithmic scale, so it's spaced closer to that than you think, right? And then what happens? Well, then, from here on, it's minus 40. Now, this is already constant going up at 20 dB per decade, but now it's going to go down by 40, or a net minus 20 dB downslope. And this is what the output will look like, regardless of the frequency. Which frequency does he want the thing evaluated at?
He wants it at 50 times 10 to the 6th.
Now, this, you're going to have to be attentive to. People mess this up. They see that drawing, but they don't know how to do this calculation. So let me get this out of here. I figure if I can do 4 or 5 problems today, you'll be set. You'll be solid with this stuff. But you'll have a lot of questions the first time you go through these. I promise you. Yeah.
That drawing right there, the end is at negative 20 dB. Far right.
Yeah. And you know why it is, right?
Right, it's negative 20.
Because we are going up at 20, then down by 40, and they're additive, so the net effect is down by 20. Correct? Yeah. From here to here it is, yeah. And then it goes down by 20. Because remember, this is added to this. This is continually going up at 20. This, you take this plus this here, it's going up at 20. This and this flat, this and this minus 20. All right. And he asked for the value at 50. Please be attentive here. At 50 times 10 to the 6, he wants the value. Now, listen, please. Just listen to me. Here's how you get that. You find the value at some point where you know it. You know it at 20, right? And it's got to be on this line right here. It has to be. So please watch this. So here it's going to be 110, right? And that's dB microvolts. Then you take minus 20. That's the rate that it falls, right, per decade. Got it? And then you're going to take the log of the frequency you end up at, which is 50 megahertz, over the frequency you started at, which is 20. And now you're going to have that value right here. You'll notice if we went a full decade, we would go from 20 to 200, right? Then you would have the log of 10, which is 1, and you would have 20 dB down. We didn't go a full decade. We went a partial, right? We went to 50, so it's the log of 50 over 20. Does everybody see how you scale these things? And you've got to see this. And it happened. This is so useful on so many things. So what do you get for this? This is what the level will be. I don't know what it is. Is that what the answer is? 102? Is that right? Okay. Now you all see that, right? Yes, sir. Sorry? That was the level here, right? Or 110? No. Well, let me put it to you this way. That slope was 40 on the input, but it's 20 on the output because we got a gain. It's going up at 20 dB per decade. Everybody got that? And that's it. Yes. It's not divide by 20. You just multiply by 20 here. Oh, this is where you start at. This is the frequency we start at. See, it's flat through here. You come to the point, you know the value. You know it's 110 there, right? That's the start. And now from here on, it's falling 20 dB per decade. So we simply go ahead and say minus 20 times the log of the difference in the frequency you stop at compared to the frequency you start at. Does everybody see that? That's the way it is, gentlemen and ladies and gentlemen. It's not hard to do this thing at all. But you have to understand it. Now, the next problem I want to do, I gave you that problem. Does everybody, any question at all about this? We're going to do another one. All right, this one is 3.2.1. And let me erase everything and get through this. Is our game still at 6? How cold? Not 20.
No, 29-ish.
29 at kickoff? 45, all right. Let's see, that's tolerable. I can live with that. Listen, I've been in that stadium when it was windy and really cold, and I couldn't get out of there fast enough. I was frozen. If you're on the upper deck and you get caught in one of these windstorms when it's cold, it's brutal. All right, now the next problem we're going to do is a more typical problem. Here we have a filter network, and here you got a resistor in series with two capacitors. I'm only going to put one capacitor there. You got a resistor here, and then you have a single capacitor. This is actually two capacitors in parallel. I think this is 70 picofarad. Is that right?
It is 50.
50 and 20, right?
It's a 50 and a 20.
Yeah, it's 70 picofarad. This resistor, is that 1K?
It's 100K.
100K.
Sorry, 100 ohms.
100 ohms?
Yes, sir.
Is that right?
It's 100 ohms.
Make sure it's right. 100 ohms.
I'll make sure.
That's an odd value for. All right, 100 ohms. Then we have the signal coming in from a source right here, right? And it's a clock. And the way they always usually draw a clock is a square pulse, something like that. So you'll know it's not a signal generator at a given frequency. The frequency you're going to see here is going to be the frequency of the clock, or 1 over the period. You all understand that? So what do they give you for this frequency?
10 mega.
So the fundamentals 10 megahertz. Is that right? So it's 10 megahertz. Now just hang on. And then they give you tau over t, or the duty cycle, which is 50%?
The D cycle's 50%.
So that means this is 0.5, all right? 0.5 is 50% if we talk in fractions, right? And it would be 1/2. Then after that, they give you one other thing, the t rise. Now this is the important one, t rise.
That'll be 20 nanoseconds.
20 nanoseconds.
And rise equals,
What?
rise equals fall time.
Yeah, and that's always typical. You find the shortest of the two and use it. That's the thing. You always find worst case, shortest of the two. Now, they want this output right here, I think, right? Is it for what harmonic?
They want on the 11th.
All right, so they want this. They want 20 times the log of the magnitude of the output voltage at that frequency, the 11th harmonic, follow me? But it will be in dB microvolts if you look there, the answer. You all see that? This is important that you go with me on this problem completely. Now, when I do this problem, this clock right here, we can take a look, and I want to make sure you see this. What this translates into is this. By the way, is it a 5-volt amplitude? So 0 to 5 volts. So what I'll do, actually I'll put it over here. Right off the bat, I know my amplitude is 5 volts. Got it? Second thing I do is sketch the waveform, and I'm going to do this in the frequency domain, in F, right here. And now what I do is come here, and where this, we're going to enter flat right there, because this is the input. This is going to be my 20 times the log of the magnitude of x of omega, think of it that way, over 10 to the minus 6, so it's in dB microvolts here. It comes in, and this value is going to be right here. This flat part is going to be 20 times the log here of the magnitude of 5, right? Duty cycle is 1/2, but then there's the factor of 2 that comes in, divided by 10 to the minus 6. Now, the 1/2 has to do with the duty cycle, right? It's tau over t. The factor of 2 comes in because that really is the coefficient of the cosine series. And remember, we took the Cn value from the series that was doubly infinite, that went from minus infinity to positive infinity. Then we made it a series that just goes from really 1 to infinity plus C0, right? And that value has the factor of 2 in it. Do you all see what I'm talking about? So that comes in there. So I have 5 times 1/2 times 2, or really 5, right? Over 10 to the minus 6 times 20. Can somebody give me that value? Just take 5 over 10 to the minus 6, take the log of it times 20. Log base 10, by the way, not log base e. That's a big problem. In MATLAB, listen, in MATLAB, if you type log, it's the log base e. You have to put log 10 if you use MATLAB. Is that the same in Octave? Does anybody know? Or Python? In Python too?
Yeah.
All right. Which is a pain, because log usually in engineering, the default is base 10. ln is the natural log, typically. What is it?
133. 134, really.
20 times that? 134? That's about right. Call it 134 dB microvolts, right? Now, the first break frequency right here will be 1 over pi tau. So we've got to get tau. And how do we get tau? Well, look, t is equal to 1 over f naught, or it's equal to what? This is 10 to the 7th, so it's 10 to the minus 7th. Does that make sense to everybody? Seconds, correct? Now, tau is 50% of that, or it's going to be what? 5 times 10 to the minus 8 seconds. Do you all agree with that? Class? All right, now if we have that, what is this? So what is 1 over pi tau? Just tell me. You've got tau. Tau is 5 times 10 to the minus 8 times pi, 1 over. 6.36 megahertz, something like that?
6.37.
All right, 6.37 megahertz MHz, okay? Now the signal comes down at minus 20 dB per decade, right? The next frequency, does anybody remember where it is? We're going down at 20. When do we start going at 40? Tau rise, exactly. Make sure you keep that in your mind. And I try to get you to repeat this stuff so it stays with you. So this is 1 over tau rise times pi. And what is that frequency? 30-something? I'm not actually sure. Tau rise is 20 nanoseconds.
16 megahertz.
Is that 16? Anybody? Confirm? 16 megahertz? Okay. 16 megahertz. And then it starts going down at minus 40, right? So we've got the initial waveform analyzed. Now we need to do the filter. I want to make sure, do you all see this, class? You're getting the same answers, right? I would draw this, and I'm trying to do it. Make sure you do a bunch of these so it stays with you. It's easy to mess these things up. Now when we look at h of omega, we're in the frequency domain, and remember, h of omega is equal to v out of omega over v in of omega. And for us, we're really going to do a transfer function. This is input, that's output. Do you all see that? Class? All right, now, when we do it, what do we get? Well, when I look at this thing, the impedance right here is just 1 over j omega c, correct? just leave this as r for now. So when I take a look at this, I can say that my transfer function, h of omega, and watch this carefully because this is the one people have a problem. They mess this up, and it's very easy, but people mess it up. When I look at this, I can say that that's 1 over j omega c. That's the output impedance. When I take a look at the output voltage to input, it's simple voltage division, right? Impedance of this divided by impedance of the sum of these two, regardless what the elements are. Doesn't matter if they're inductors, capacitors, or resistors, right? As long as it's impedances you're adding. So I have 1 over j omega c divided by 1 over j omega c plus, in this case, r. Now, what I recommend you do, because when people put it this way, they tend to mess this up when they leave it like this. Go ahead and multiply everything through by j omega c, top and bottom. By doing so, you get rid of it here. Follow me? And then you're left with 1 down here. You're left with this. 1 plus j omega r times c. Can you all see that? Just so everybody's together on me, right? Now, that is still in omega. So, what I typically tell people, you can leave it in omega if you want, right? You can. But it'd be a bit cumbersome. What I do is I'll say, take this, and then let me work right here. I'm going to take, and I'm going to put omega as 2 pi f. So when I take 20 times the log of magnitude of h of omega here, I take 20 times the log of 1, right? Of just 1. I'm putting it down for completeness. And then it's minus 20 times the log here of the magnitude of 1 plus, and then it's going to be j 2 pi f times r times c. You all see that? I just replaced omega with 2 pi f. Correct, class? Take a look. Can you all see that in the back? I always worry because I don't. Can you see it? All right. Make sure you can read it and you understand what I've put here. Now, at that point, what you take a look at is, well, 20 times the log of 1 is 0, right? Do you all agree with that? So we don't need that. So we got this right here. And that is the filter right there. So my output, now we take a look at where we want where they want the output at, all right? What frequency do they want the output on?
They want it at the 11th harmonic.
Okay. This is important too. This is the first harmonic. All right? The 11th is simply 11 times that. So the 11th harmonic is equal to 110 megahertz. Do you all see that? Good? If the first is at 10, and you multiply that by 10 megahertz by 11, you get 110 megahertz. Okay? That's all it is. There's nothing tricky here, but sometimes you can interpret these wrong. I'm just going to tell you you can. So now I come down here, and when I actually look at my output, as of before, I take my input signal here in dB microvolts, and I add to it 20 times the log of the filter at the frequency of interest. Follow me? Follow me on this one. So I'm going to say V out of the 11th harmonic, or F equals 110 megahertz. I'm going to put it this way, and it'll be in dB microvolts. Is going to be the value of this at 110 megahertz, right? Now, please pay attention here. This is important. So when I'm doing this, I know I've got 134 dB I'm starting at. Correct, class? Now, please watch this part. There's this. People mess this up. Well, let me just show you. We got to find out where 111 or 110 megahertz is. It's somewhere out here, right? 110 megahertz would be somewhere out there, correct? So we know we're going to 40 dB per decade slope. Do you all see that? You with me on this? We're out past the 20. We're into the 40. All right? That's where we want the information. So how do we get it? First, we start with that 134, right? That's 134 dB microvolts. That's where we started at. Then we go down to here at a rate of 20 dB per decade. So I take that minus 20 times the log of the frequency I stopped at, which was 16 megahertz, divided by the frequency I started at, which was 6.37 megahertz. You all see what I've done there? I could put the megahertz in, but they cancel. Class, are you with me? Stay with me on this one. We're not done, right? We've got to go to 110. But the rate of slope there is 40. So now we take minus 40 times the log of the frequency I stop at, which is 110 megahertz, the 11th harmonic. So it's 110 megahertz over the frequency I started at, which is 16. This is real important. This is really MC stuff. Over 16. Now that's what the value of the input signal will be coming into the filter, right? But we also have to add the effect of the filter. Now the filter, remember we had log 1 up here because it's this thing right here. So it's going to be minus the log this at 110 megahertz, right? You can ignore that 1, I think. So it's going to be minus, and that's 20, right? In front of there. You all see that? Minus 20 times the log here. And then it's going to be 1 plus j 2 pi. It's the magnitude of this, 2 pi. The frequency is 110 megahertz. And then times R times C. Now the RC is given in the problem. R is 100 ohm and C is 70 picofarad, right? Here's what you do on this one. Calculate this by itself. Just tell me what that value is. Hopefully it's much greater than 1, but I can't promise you that. I want to know the value. Just tell me the value. Anybody else?
I got 4.84.
Anybody else? Yeah, it's 2 pi, 110 megahertz. Huh?
4.84.
4.84? Well, that's not a whole lot larger than 1, but it is larger than 1. So what's normally done is this. If it's larger than 1, you get rid of that. It should be a factor of 10, but in this case, we're going to make an exception. You could add the 1 into it, take the absolute value, then you'd have 1 squared plus that squared, square root of, because it's 1 plus j something. But you can almost forget that 1. What do you get for this, I think? Minus 13.6? This right here is for the whole thing right here? 20 times that?
Yes.
All right, so this is minus 13.6 dB microvolts. Now go ahead and do this. What do you get for this one? And I'll try to put them down. For this? Is it, when you do the whole thing, you get 92.5? Is that what you said? Yes. The entire output, it's 92.5. What did you say? 92.5 or minus 92?
92.5 for the left 3 terms.
Okay, and then you got to subtract 13.6, right? So all these added together are 92.5 dB microvolts. And minus 13 is going to be
78.9
dB microvolts. What does he have? And I don't know this one. I think it's right, but is that what the answer is that I posted in class? Is it?
Yes.
All right. You all see what I did? You can ask me.
78 is the final answer. 78.56 decibels.
We got 0.9. I tell you the truth. When you're talking about tenths of dB microvolts and the answers of the order of 70, 80, you don't worry about it.
Okay.
All right. And you always look for worst case. Now that tells me what the output's going to be for the worst case output for that at that frequency. And by the way, when you get at high frequencies, all right, really at that point where there's an 11th harmonic, 12th harmonic, if you look on the spectral analyzer, you don't see discrete lines. Theoretically, you would have discrete lines, but you don't see that. It's a continuum. This is what you'd actually see in the spectrum analyzer, more or less a curve like this. Something else about a spectrum analyzer, you're not going to see just this shape. You'll see this. There'll be noise. It'll be bouncing around all the time where it actually goes up, down a little bit. Okay? Yes?
So we don't do the 1 plus J 2 pi?
You don't see what normally happens is you're at a frequency, if you're close to 1, if the 2 pi r 2 pi f times rc is of the order is about 1, then typically you don't even include that because the magnitude of 1 plus j1 is 1.4, right? The log of that is about 0. So you don't worry about that. All right. Now, next one. Which one? Yeah, we can do it. What's the number on that one?
3, 2, 3.
While I'm doing this, since there are 2 tests, are there any really big games besides ours?
There's another big one. We don't have one, don't we?
I think they're playing next week.
Next week, not this week.
Yeah.
That'll be awesome.
I'm going to show you a trick on this one too.
Oh, Georgia and Florida are playing at 2:30.
That's right. They're playing in Gainesville, aren't they? I'm sorry. Where's the neutral field? Jacksonville. So like Tuscaloosa would be neutral for us, right? I've never been to that, but they've said since I was a young boy that was the biggest cocktail bowl in the world. Apparently, it's just one big circus there. What's this value? R equal.
1K and 400 picofarads.
This is C equals 400 picofarad.
Yes.
And what about this one?
And then 1K.
All right, good.
Although they have it switched, but they're parallel.
Doesn't matter. And they want this output, right?
They want the out of that person.
All right, give me the specs for this.
You've got a waveform of a, let's see,
Just give me the fundamental frequency.
10 to the 5th radians per second.
Oh, God. A meganaught is 10 to the 5th radians per second. And what is A?
A
5 volts, 0 to 5?
doesn't say. I assume so.
Well, what does he want? Let's try that.
He wants the 50th harmonic.
Oh, he gives you a drawing. We can get it from there. See, he's got that. Don't worry about it. So he's got VS, and he has it at specific values. The center, is that 10 to the 6 right there?
Yes, 10 to the 6.
All right. Let me try to show you. He gives you this value of VS. He goes ahead and he plots it in the frequency domain for us. And he has this. He has an envelope like this. And he has dead center is omega naught is say it again, 10 to the 6?
6 is the W center.
So it's 10 to the 6 radians per second, right? And then he's got, is that every 10 to the 5th?
Every 10 to the 5th, yeah.
No, omega naught's 10 to the 5th.
Is that different from the 6
No, what he's saying is this is 10 omega. Omega naught is down here. That's 10 to the 5th. Omega naught is 10 to the 5th. Then he's got like 2 omega naught, 3 omega naught, and then he has this one down here as 10 omega naught, which is 10 to the 6th. Follow me? If omega naught is 10 to the 5th, 10 times it is 10 to the 6th. You follow me? Then he has lines down here. He's got a bunch of spectral lines, as I can tell, right? And what does he want? So this, and what's the peak here?
The peak, he doesn't give you the peak. Oh, it's 120 dB.
120 dB microvolts. And minus 20? Or plus 20, I mean?
Yeah.
And minus 20. Okay.
That'd be minus 40.
Minus 40. Uh-oh. Different. minus 40 dB per decade. All right, and go ahead now.
And it starts at 100 dB.
Well, no, it's 120 right there. That's all we need to know.
Peak, okay.
That's all we need.
The 50th harmonic.
He wants what?
The 50th.
Of the output.
Just says determine level of the 50th harmonic. Is the output.
Yeah, but he's got a circuit there, right? So he wants the output voltage at the 50th harmonic. He wants this at a frequency of F equal to 50 F naught. That's what he wants. Or omega equals 50 omega naught. Do you all follow me on this, class? Please watch this one. You think you see it. There's something subtle you don't see, and on a quiz test, it breaks you apart. You just don't know what to do. So please, and if you have questions, ask the questions. So for this one, identify where he wants the actual output voltage. That's at the 50th harmonic, which would be 50 omega naught. So whatever that is, 50 times omega naught, or 50 times 10 to the fifth, or really at 5 times 10 to the 6th radians per second, right? Y'all agree with that? It's 5 mega radians per second. That's where he wants it, right? Now, he gives us this as Vs, right? So we're going to get that level. What would that level be? Think about it. This is 120 dB, right? We're going down at 40 dB. To get the level here, what do? Well, we start here, right? We take 120 dB, oh my gosh, dB microvolts, and we subtract what? Minus 40, let me finish this one. Minus 40 times the log of what, people? The frequency you stop at, right, which is 5 times 10 to the 6th, right, over the frequency you start at, which is 1 times 10 to the 6th, or just 5. So that's the value here of the input, right? Now, when you look at that filter here, this is the way I tell people to do it. This has a characteristic impedance. I can call this ZRC. Are you with me? Now I can say that my filter here, H of omega, is really equal to ZRC over ZRC plus R. If you take a look at that, the only thing I've done is eliminated the 1 over j omega c plus and the R thing in parallel. So I just simplify it, right? Now I divide by that impedance by ZRC, and I get 1 over 1 plus R divided by ZRC. But what is ZRC? Right here? Well, what would ZRC be? That's going to be 1 over R plus j omega c. Correct, class? Do y'all agree with that? So if I take 1 over that, I have 1 over R times j omega c. Or plus j omega c. Now you can see what happens here. I have R by R is 1. 1 plus 1 is 2 plus j omega RC. Do you all see that? I'm out of time here, but you can take 20 times the log of that with omega replaced by 5 times 10 to the 6th. Do you see that? And you're going to get a minus, because the log of 1 is just 0, and then it's minus the log of that. Evaluate at that frequency. See if you get the answer in there. I hope you understand. I'm trying to just, by showing you problems, how to do them, really revealing a lot of the theory. And I said you weren't going to get quiz today. You have 2 tests. On Monday, you're going to get quiz on this stuff, all right? Fair enough? All right, have a great week.